All right, I think we can go ahead and get started. We have 34 people on the call. Can everybody see my screen? Can you see Jeff?
Yes.
Awesome. Okay, yeah, so welcome to the February 9th connectivity call. Pretty excited for the speaker today. We have a awesome presentation on water heater control strategies, but first up, as always, we have our welcome and intros. We got to read the antitrust statement. We have a couple cool AWHI updates, and then, as I said, we're getting into that presentation, and then we'll spend the last few minutes with an open floor, just any questions you have on the presentation, and then just kind of wrap up next steps, whatever we want to talk about next. So if anybody has not been on this call before, is new to AWHI in general, feel free to turn your camera on for a second and tell us who you are.
Yeah, we're not going to go around and introduce everybody. There's just too many people. So.
I'm Jeff Howard with Connecticut DEEP.
Nice to meet you, Jeff.
I haven't been on in a while, but have been here before. Rolf Bienert with the Open ADR Alliance. Hi there.
Awesome. Hey, Rolf.
Okay, let's
Thanks,
keep
y'all.
moving then. Yeah.
All right. Antitrust compliance statement. Jeff, you want to just go ahead and read that one off?
Sure. The Advanced Water Heating Initiative is a member-supported collaborative of professionals from across the country, across the U.S. This diverse membership includes numerous competitors, and care must be taken to scrupulously abide by federal and state antitrust laws. Members should remember that antitrust compliance is important at all times. At this and other AWHI meetings, participants should not discuss competitive pricing, profitability, allocation of markets or customers, or promotion of a particular product or accessory.
Sweet. Thanks, Jeff. All right. So a few AWHI updates. There's this very cool new efficiency main heat pump water heater diagram. I imagine it's a decent thing to use on reports if you cite efficiency main or get their permission, but always just nice to have more good diagrams because we know how many confusing infographics there are out there. There's also an AWHI installer task group kicking off pretty soon, so that'll be a great opportunity to have view collaboration between installers, and because they're such an important part of making this heat pump water heater market transition happen. And if you're interested in that, definitely email info@awhi.org. And then hot water forum sessions are coming up soon too, so that's very exciting, including I'll be presenting. There'll be a presentation from Lily, who's going to be giving the main presentation here today, and a bunch of other connectivity related calls. So not sure if that's being recorded or not, but regardless, at the Hot Water Forum, there should be some very cool sessions. So I hope to see some of you there.
Yeah, just a little insight that we will not be recording and that will not be hybrid. It will be in person in Atlanta in its conjunction with the Hot Air Forum. And there are also some ancillary activities going on either side. So if you've got questions about that, reach out to ACEEE or anybody who's been around this stuff for a while. It's good stuff.
Awesome. Thanks for those clarifications. Super helpful. All right, so I'm going to turn it over to.
I'm going to pause you for a second there. Jackson,
yeah.
You had requested a couple minutes that you and I chat a little bit about this, and Dr. Bass is also on. I don't know if Dr. Vincent Elmer is on as well, but let's give a little bit of an update on the security work.
Yes, thank you. Jeff, can you guys hear me?
Yes.
Great. Yeah, so Jeff and I met offline. This is a continuation of a previous item to this group, which is on cybersecurity. There was a draft that was participated by a number of contributors a couple of years ago, and there was a request or a determination that rigorous reference to the work would be required. And we had pinged P&L's cybersecurity team for such a project, and they responded with a proposal. That proposal has been reviewed, and it is definitely feasible But in parallel, Jeff had determined that since NIA already have a working relationship with Dr. Bob Bass, who is on the call, we thought leveraging some of Portland's resources in this matter could help things along in parallel. So I don't think we have determined that we're not going ahead with the PNNL proposal, but we thought, moving the ball as fast as possible, with as many references that would rigorize the work that was done would be really useful, because cybersecurity is such a huge emerging and very, very important component of the work that we're doing in this group.
Yeah, Dr. Bass, do you want to give a brief update of our conversation we had with Dr. Ilmer?
Yes. So I'm not a cybersecurity expert, so I do have colleagues who work in the area. So I struck up a conversation with Dr. Vincent Imler at Oregon State University, who does work in cybersecurity and has a particular focus on hardware and tampering, which is pertinent to the EcoPort. So we have an initial conversation with Jeff, and we're going to move forward with putting forward some ideas to get Vincent involved in reviewing the cybersecurity protocols.
Yeah, a little bit of color on that, and I really appreciate the introduction, Dr. Bass. Where he's got some background. He used to work for the German national government and was actively involved with trying to figure out the vulnerabilities for gambling machines. And so he has intimate knowledge of both hardware and software, and then a revenue stream on this. So it's actually kind of a perfect storm. And he had a lot of interest in, and I think we're going to move forward with this, of having his students do a hackathon on it. And so we're going to try to break these things. So we're going to raise the bar and then see where our vulnerabilities are, and then make some recommendations. This is not to be punitive to any one of the players. It is to be informative and make sure that our utilities can back down off their worries, because there's a high worry factor right now with some of our utilities.
Yeah, actually, to add to that, I think PNNL also has a rigorous, what they call red hat team. It's kind of like, Spy versus Spy, for those who are old enough to remember Mad Magazine's Spy versus Spy. But that's kind of so the red hat team is kind of like what is being described here. No, Jeff, if I could also, Jeff, we also talked about one other thing, so I'll just need an extra 10 seconds or so. There's some work that the AEA group, which is the contract manager for Water Saver, along with PNNL and eRadio, has been working on offline on ALU, advanced load up, and we've gathered a ton of material that at some point we'd like to give a heads up that we're working on it. We're cleaning it up. At some point, I think the AWHI membership would be very interested in some of the findings there.
Yeah, that's great. Tristan.
Yeah, on the security side, I mean, look, right now CTA 2045 is only a standard between the water heater and the module. And this is a question. So if I want to confirm that to hack CTA 2045 initially means you're hacking the connection between the module and the water heater, which means you've got one water heater that you've hacked. So it's a little bit absurd to worry about that. So the next level is, well, okay, now you have a CTA module and it's communicating obviously to a cloud, otherwise there's no benefit. And now that's where all of the potential security risks come in. And each company that makes a module essentially needs to be evaluated independently. So if you guys are talking about a hackathon, I just want to confirm you're essentially saying we're going to try and hack everybody's platform who makes a module. So that's two questions. A, if you hack the actual CTA 2045, you're only hacking between one water heater and one module. And B, if you're going to do a hackathon, you're actually testing the security of every module maker.
Well, actually, there's one more view, Tristan. I think certainly the CTA module to the cloud is one of many connections. I think Bruce Norman had that diagram about the multiple access into, the water heater. So the other thing that Jeff and I, along with some of the other groups that I previously mentioned, are starting to look at is the central versus distributed computing model, which also addresses some of the security issues that's being addressed as well. So, for example, in the centrally computed model, what you're citing is absolutely true. In the distributed computing model, that may or may not be true, because if the information is coming in to advise the individual water heater to optimize, information may or may not be coming back, or may not have any other access into that entity. So these are all kind of integrated, they're all related. So that's a great point to be raised as well.
Well, just to help everybody on this call sort of be really clear, because some people are going to be less familiar with all these issues, right? Once you have a module on a water heater, and this is good for Internet of Things, for all Internet of Things, right? Once you have an Internet of Things device, it can be talked to from outside the device. So for now, that's the module. Although let's all remember that some water heaters are being managed by the OEM cloud through an API. So conceivably, those should be tested for security as well. But once you have anything that's communicating outside itself, which is the point of all this, then it either communicates to a cloud or it communicates to some other typically local entity. And when Bruce talks, that's usually a local gateway, some kind of local computer. And some IoT companies, they try to never allow local, and because they want to guarantee that it always goes only through their cloud. And in fact, it's super interesting to try and find things like thermostats or other things that allow local control so that a local gateway can optimize it. And Bruce Norman talks about receiving prices. So that's it. Like, that is it. If you're going to do a hackathon, you have to either try and hack a local connection if it exists, or you have to try and hack the entire cloud platform that almost always exists in any Internet of Things company. Just want to be really clear.
No, well,
Hey guys, this is Julian from Bradford White. I'd like to make a quick statement on this. So Tristan's point is extremely valid, and I think that, just in general, and I'm only speaking from my point of view, given that our product does also connect to a cloud, is that I'd appreciate if you guys, at least prior to the hackathon, come up with some type of scope of exactly what you're trying to look at here. Because to Tristan's point, you could just continue going down rabbit holes over and over and over again to get to other stuff too. And if this is truly just about the EcoPort hardware connection, that's a different story than going through fully to someone's cloud. So just wanted to point that out, that I'd appreciate it at least ahead of time, depending on who's participating, that you have some type of scoping of what this looks like.
Julian, I appreciate the comment, and of course, lots of transparency. We wouldn't have brought it up if we weren't going to be sharing the conversation. So those of you who are interested, let us know, and we'll definitely bring you into that conversation. It's not going to be done in a dark site someplace. It's going to be fully transparent.
No, absolutely. Yeah. Look, whoever's running it, I don't know, Jackson, if you're the one necessarily running it, but let me know, and Bradford White would happily be able to.
Yeah, and like I said, I think the fact that all these questions are raised are excellent. I just want to have one more point of clarification relative to Bruce's diagram. There is a direct connection between, say, something like a Midas server to the device itself without necessarily having a local optimizing engine like home energy management and so on. The device itself, and in some case, in the context that Bruce and I had talked about, the UCM could actually perform a lot of the computation that does not necessarily have to go back to the cloud. So anyway, like I said, these are really, really fine points. And I think it sure sounds like we're going to need to have a whole bunch of other discussions on it. But absolutely, all these things will be transparent, and lots of food for thought for the effort with Bob Bass's crew as well.
That's an excellent point, Jackson. I'll just wrap up with the fact that, yes, notice that if the device goes straight to a Midas server, it's also going outside itself. And I doubt very much that we're ever going to want a module that's just never talking outside itself and just optimizing a water heater for 10 years without ever talking outside itself. So it's about testing the security of modules or even water heater OEM stuff outside itself.
Yeah, great. Noah, thanks for the break in this. So let's get back over to Lily and go on with that. So
yeah, absolutely no problem. And thanks for sharing all those thoughts. Super cool update. All right, Lily. I'll just keep sharing a screen just for the recording's sake, but just let me know when you want me to switch the slide.
Awesome, sounds good. So yeah, my name is Lily Buechler, and I'm a graduate student at Stanford University in the Department of Mechanical Engineering. And today I'm going to give a quick overview of a research project which is focused on using a specific type of control strategy, which is called model predictive control for water heater load shifting. Next slide. So in this work, we're really focused on control strategies that allow individual water heaters to respond to time varying electricity prices using a strategy called model predictive control. And model predictive control, or MPC, is different from many load shifting strategies that are being used today in that it's an optimization-based approach. And so this controller is essentially solving an optimization problem to figure out how to best shift load to minimize costs while also respecting things like thermal comfort. And so one of the benefits of MPC over other load shifting approaches is that it's a predictive controller. And so it can anticipate how electricity prices might change in the future, anticipate how a user might use water in the future based on forecasts, and then make decisions accordingly. And so because of this, MPC can be really effective at dealing with more complicated load shifting scenarios, beyond just simple time of use pricing, where load shifting can be pretty straightforward. So in the future, if we have dynamic pricing, or if we want to optimize around other continuously varying signals, like carbon emissions, then we need ways to automatically translate those continuously varying prices or signals to control actions that also account for water heater demand for an individual consumer. And so MPC is basically one approach in order to do that. And so there's been a lot of different academic papers looking at how to develop MPC strategies for water heater load shifting. And there's been a couple of big projects at national labs over the last few years that have kind of looked into this, but there's still a lot left to be learned about how these controllers would perform on actual water heaters and kind of better understanding their advantages and disadvantages. So in our research project, we've done a lot of testing of these algorithms in a laboratory testbed environment and learned a lot of things about how we can better design them for kind of real world situations. Next slide. So this is just a overview of how an MPC strategy could be implemented on a water heater. The main idea is that the controller is solving an optimization problem to find the optimal heating schedule, which reduces costs and maintains thermal comfort for the consumer, given different pieces of information. And so that includes things like time varying electricity costs, as well as a model of the tank thermal dynamics. So basically a model saying how the tank temperature is relating to heating and water draws. And then it also uses temperature measurements from the tank, as well as forecasts of what water draws are going to be in the future. And then the outputs of that optimization problem is essentially a sequence of on-off control actions for the heating elements or the heat pump, depending on the type of water heater. And so this is an algorithm that would repeat iteratively, say every 10 or 15 minutes or so, where it would measure the water temperature, forecast future water draws, solve the optimization, set the control actions, and repeat. Next slide. And so the details on how you would set up one of these optimization problems can really affect how well the controller performs in practice on actual tanks. And so the optimization problem looks something like this, where the goal is to minimize some cost function, which for load shifting is typically electricity costs. And then that optimization is subject to different constraints, which ensure thermal comfort and kind of encode different characteristics of the water heater, such as the amount of power the elements can consume or the heat pump, and a model of tank thermodynamics, which models how tank temperatures relate to power consumption and water usage. Next slide. And so what we found from our lab testing is that there's kind of two important design choices which can really affect how well a control strategy like this performs on actual tanks. And so one of them is which model that you would choose to use of the tank thermal dynamics in this optimization problem. So this model is essentially telling this controller what the current state of charge of the tank is and how that state of charge will evolve in the future based on control actions and water draws. And so in the past, previous studies tended to use really simple models that ignore real world tank stratification. Most water heaters are thermally stratified, meaning that there's different layers of temperatures of water in the tank, but accounting for that stratification in an optimization-based controller makes the optimization problem a lot more complicated. And so we wanted to understand how much this model fidelity really matters, and how it affects control performance and what that trade-off is with computational costs. And then another important design choice is how you forecast future water draws. So in a lot of water heaters, you probably aren't going to have a flow meter, which actually measures the water draws. And so you would have to estimate them based on other sensor measurements, like temperatures. And so we analyze the best way to do that. And then in terms of forecasting future water draws, you want a controller which is really robust to wrong forecasts, just because water use patterns are very variable. And so we wanted to understand how variability in water use patterns between consumers and for the same consumer can affect control performance. And so in this project, we tried to answer some of these questions by comparing different model predictive control strategies through laboratory testing and simulations. Next slide. So for the first phase of this project, our focus has really been on 2-element resistive water heaters. We've also started doing some work on heat pump water heaters, but the results I'll show today are just for resistive. So this is a lab test bed that we set up, which is part of a larger kind of smart home test bed that we have here at Stanford. And it includes a 50-gallon Rheem 2-element resistive water heater, which we completely rewired so that we have independent control over the 2 elements. And we also installed a bunch of temperature sensors, a flow meter, and a valve actuator so that we can automate flow profiles using actual data. And then all the controls are running on a Raspberry Pi unit. And so this setup lets us run long-term tests using basically any control strategy that we want in a very controlled environment. And so we can compare the performance of different controllers using the same exact draw profiles. And then we also evaluated different control strategies in simulation by essentially calibrating a pretty detailed model of tank thermodynamics to our lab measurements. And so that lets us test a much larger number of control strategies and scenarios. Next slide. So the first question that we tried to answer was, how does model fidelity affect model predictive control performance? And so for this, we compared 3 different controllers: a baseline controller, which is just doing thermostatic control using no load shifting. And then we compared that to a model predictive controller, which uses a super simple model of tank thermodynamics, which essentially assumes that the tank is fully mixed at a uniform temperature, which obviously isn't accurate, but it is the most common approach used in studies that have tested MPC strategies in the past. And then we compare that to a model predictive controller that we developed, which uses a model which very coarsely accounts for tank stratification while still being pretty computationally tractable. And it basically splits the tank into 3 different regions. And we chose this model specifically for 2-element resistive water heaters and the types of stratification patterns that you can see in these tanks. Next slide. So we ran a set of laboratory tests comparing these different controllers, where each controller was tested on 3 different water flow profiles that have very different daily water usages. So that's a total of 9 different tests, and then we ran them each for 4 days. And for these tests, we assume that the controller has perfect knowledge of what future water patterns are going to be, just so that we can analyze the effect that the controller design and the model is having on performance. And so what the controller is doing here is optimizing over a 24-hour period in the future. So it has access to 24 hours of future prices and forecasts of water use patterns, and then it updates every 10 minutes. And we use the time of use profile, which has a peak window from 5 to 8 p.m., which happens to coincide with a lot of the water draws that are in this data set. So some of the results are shown here on the right. In these figures, we're plotting different metrics. So energy consumption, the outlet temperature, cost, and the average cost of electricity as a function of daily water usage for different scenarios. And the open circles are our lab test results, and the solid lines are simulations. And so we saw really similar results between the lab tests and simulations in terms of energy consumption, temperatures, and the timing of when the water heater is turning on and off. We also saw really similar energy consumption and energy efficiency across the controllers, which is what we would expect, just because this is a resistive water heater where the efficiency is relatively constant. But for load shifting, we found that our higher fidelity MPC controller was way better at reducing costs and shifting load than the simpler model predictive controller or our baseline. And so this plot here on the bottom right is showing the average cost of electricity consumed by each controller, and you can see that the more complicated one is able to shift all the load to the off-peak time period, where the simpler model, because it uses a more inaccurate model, it tends to significantly underestimate the amount of useful water in the tank and ends up reactively turning on when prices are more expensive, even though it doesn't really need to. And so I guess the key result here is if you're using a model-based control strategy where you're solving an optimization problem that uses a model, it's important to use a good model. And so for these water heaters that have a lot of stratification, it's important to use a model that at least coarsely captures some of that stratification. Next slide. And so for those previous tests, we assume that controllers have perfect knowledge of what water use is going to be in the future. And of course, in practice, that is never true. And often we can't even directly measure water flows unless you have a flow meter on the water heater. But what we found is that you can pretty reliably estimate historical water draws just using power and temperature measurements, as long as you have a decent model of the thermodynamics. And then you can use those estimates for forecasting future draws. And then in terms of integrating these forecasts into this control strategy, one thing that we've learned is that over-predicting draw volumes is far better than under-predicting in terms of both thermal comfort and load shifting. So if you use an approach where you're using really conservative forecasts that are estimating water draws most of the time, then that can be pretty effective at preventing runout events. And so this plot on the right is just an example for a specific home, which is using a PG&E time of use rate, the effects of using different controllers and different forecasting strategies on performance. So for this specific example, we were able to reduce costs by about 19% through load shifting, while having the outlet temperature drop below the set point only about 2% of the time. Next slide. So what is actually needed to implement a model predictive controller on an actual water heater? Well, in our kind of proposed implementation, we use 3 temperature sensors, 2 power measurements, so 1 for each element, but we don't need a flow meter. And so every part of this architecture, from learning these models to forecasting future flows to solving this optimization, you can do with just 3 temperature measurements and 2 power measurements. And then in terms of computational costs, traditionally one of the downsides to using model predictive control is it is a lot more computationally expensive than like a simple rule-based control strategy. But in this work, we used a pretty low-cost Raspberry Pi to do all the computations. And for each one of those optimization solves, it took less than a second to solve. And so it's definitely a strategy that's implementable on a low-cost microcomputer. It's not necessarily something you would have to run in the cloud or with a more expensive computing device. And we also use only open source solvers for all of these computations. And then in terms of power controls, we basically assume that you need to have independent control over the two elements. Next slide. So just to summarize, kind of the main focus of this work was to better understand how certain design choices will affect the performance of a model predictive control strategy for water heater load shifting. And we found that it's really important to account for tank stratification in the control model. So in this work, we focused on 2-element resistive water heaters and kind of developed a strategy which works really well for those types of water heaters. But different water heaters have different designs. You know, a heat pump water heater has different design than a 2-element resistive. And so a strategy that works well for one type of water heater might need to be adjusted for a different type of water heater to work well. And so in the future, we're hoping to look more at heat pump water heaters, as well as look at other types of use cases like dynamic pricing or PV generation following. Next slide. So if you're interested in learning more, we just had a paper that was accepted to IEEE transactions on smart grid. And there's a paper, a preprint available on ARXiv. So if you're interested in looking at more technical details, feel free to check that out. I just wanted to acknowledge my co-authors and funding sources, and we'll be happy to answer any questions.
Awesome. Thank you so much, Lily. That was great. Jeff, I think you're muted.
Great work here, and I think there may be some questions by some of the manufacturers either on this call or directly to you. So Ben, why don't you go ahead and we'll start, and then there's some conversation in the chat we might want to get to. Go ahead, Ben.
Sure, thanks, Lily. Just wondering if are there any plans to open source the, I guess, what's running on the Raspberry Pi to kind of validate these results or reproduce them ourselves?
Yeah, so I guess the mathematical algorithm is published in a paper, so that is publicly available. I think at some point we might release the code in like a GitHub repo at some point, yeah. I see a question here. Did you test real-time electricity rate? So in the tests we've run so far, we are using time of use rates, but we're planning to run tests on dynamic pricing and other continuously varying signals in the future. So I think that's like where model predictive control could have benefits over simpler load shifting strategies, is for use cases that are more complicated than time of use. So we definitely would like to look at that more in the future.
And I'm just going to hop in.
Okay.
Sorry.
Go ahead, Noan.
I was going to say, to answer one more question too, the slides will be available after, and this is recorded, so I'll send that out too.
Jackson, you got your hand up?
Yeah, hi, Lily. I thought I heard you in your presentation say that the MPC, which is implemented by the Raspberry Pi, can be also implemented in microcontrollers along the lines of what we was just talking about right before your presentation, which is the locally distributed or locally computed paradigm. So
yeah.
So I thought you had basically affirmed what was discussed previously, which is the MPC can be implemented in microcontrollers at the device or in the UCM.
Yeah, so I mean, we ran all our tests running all the computations on a Raspberry Pi, which, you know, it costs like $35. It's pretty cheap. And I'm sure you could implement it on an even lower cost computing device. So it's definitely possible to implement these types of control strategies on a microcontroller.
Thank you.
And Chris?
Yeah, thank you. And Lily, again, I'd like to reinforce that this was a great presentation and some really impressive work. You had a slide back a couple that was showing sort of the relative cost levels of no control, simple control, more complicated control. It was all benchmarked on dollars, and I'm sorry if you mentioned that, but what time period does that dollars represent? Was that a month, a year, a week?
Yeah,
Laura,
it was
can you
a
go
few
back to that
days.
slide?
It was over a few days. So these laboratory tests that we ran. So yeah, this slide.
Right.
So this was over, I think, 2 weeks or so. And then the previous slide was over a few days. So the first set of tests that we ran were pretty short. And then the next slide, we were using a data set that was a bit longer. So I think this might have been like 2 weeks or so. Yeah, I think one thing that we have struggled with is getting like a large amount of flow data from actual homes that we can run realistic studies with. And I mean, we've gotten some data that have been published in other papers and stuff, but they're typically like a couple months long. So if anyone has suggestions on data sources that might span like a year for a lot of different homes, or we could look over a wide variety of consumer use patterns over a longer period of time, that would definitely be helpful.
You'll get a lot
I
of
don't
that
know if
at the water forum, Lily. You can talk about draw patterns the whole time you're there if you want.
Awesome, but that's it's good feedback though, that when you look at this, if that's a relatively short period, then your opportunity for payback on a fairly marginal technology investment looks promising.
Yeah. So for these time of use rates, the reduction is like I think this was for a PG&E rate. It's 20 to 30% from load shifting are the savings that you can get. I mean, using a profile where a reasonable amount of consumption is in the evening, coinciding with that peak period.
Excellent. Thank you.
Jackson, is your hand up from before or is it up again? Okay, Tristan, go ahead.
Yeah. So I just wanted to kind of totally respect the Jackson saying, hey, maybe the microcontroller can never communicate to the outside world and still provide value. There's certainly times where you can imagine high security areas like Department of Defense buildings that might say, hey, we never want anything communicating outside this building, but we'd love to have our water heater help the grid. So super interesting. But you mentioned time of use, Lily, right? And you mentioned that one of the things to try is pricing. And I just want to remind everyone on the call, right? Water heaters are time shiftable a lot easier than HVAC. And the value is so much higher when we can change it every day. Because if you look at the Cal ISO grid, even every day, the peak, the ramp, the valley, the width of the valley is really changing. So I think water heaters are beautiful when they can change every day, and time of use, I'm just praying we don't get stuck on. So just wanted to make the pitch for daily change. Thanks.
Love that.
Any other questions out there?
I saw a good comment from Dr. Bass about inferring energy consumption, and that's something that in my, in an MBI study we're working on right now, kind of inferring energy consumption without, or I guess flow without full monitoring equipment, without a flow meter. So yeah, if you want to speak to that, Lily, or if Dr. Bass wants to speak to that, I think that's a very important topic.
Yeah, basically how we've been doing it is like for the model predictive control, you have a model which relates temperature to power to water consumption. And if you're measuring temperature and power, you can invert those equations just to estimate water flows. And that seems to be a pretty accurate way of doing it. I've definitely heard of other people who under thermostatic control develop ways of estimating it just on power measurements and not using temperature measurements. So I've seen it done that way too.
Awesome, thank you.
And if I could just add to that, certainly from our data, we've never tried, but we see sharper, well, CTA 2045 not only reports power, but also reports storage capacity. And Lily, did you sort of measure or sort of use any of those storage capacity numbers that are reported for CTA 2045, or were you guys like not using CTA 2045 and just maybe the water heater API or something?
So we're not using a water heater that has CTA 2045. This is like a very dumb old water heater that doesn't have any sort of interface. So I mean, we completely like rewired it to do all our own controls on it. So we didn't test getting those measurements.
Great. And when you mentioned that, were you controlling both upper and lower element individually, or were you just cold talking the power like historically has been done?
No, we are controlling them individually. So the thermostat is not doing anything. I mean, we disconnected the thermostat for that. And so we're independently controlling the two elements based on the optimization outputs.
Super interesting. So hopefully one of your other tasks at some point, and this is a question, would you consider it important to sort of use a water heater API, which some of the bigger manufacturers have, versus a CTA 2045, and see if you get enough sort of ability to do what you've done with those avenues, since those are more readily available right now? What are your thoughts on that?
So by CTA 2045, you mean using commands like load up, shed, et cetera, in order to implement the controls.
And getting the power data and the storage capacity data from the water heater, because both of those are done as well. And just so you know, like that storage capacity data, when we see the difference between general cooling of the tank with no draw versus a draw, right? A draw, you see the storage capacity pipe up. Generally, you see the elements come on. So it would be super interesting, right? Because to scale and to be ideally of value, normally water heater OEMs aren't going to let your control algorithm like come in and replace their controllers. Could be an option, but if you could do it through control methods that exist right now, either the OEM API or the CTA 2045, I think that would be able to go to market and be useful a lot faster.
Yeah, that's a really interesting point. I think we had kind of come up with this with the idea that it would be integrated into manufacturer controls and you would have like direct control of the two elements. But yeah, it would be interesting to see like how you could potentially take the MPC outputs, translate that into control actions that could be implemented through CTA 2045 and see how that compares control wise if you can get similar gains using that approach. It's an interesting question. I don't have a good answer for it, but
yeah. And then just broader, right? Do you have an opinion right now? I mean, everybody on this call has often thought that sometimes it might be better for the grid and for the world and for the climate to actually have a lot of water heaters going in as electric resistance water heaters like you played with versus heat pumps, because they have so much more power and they heat up the water more quickly. But we know that there's a huge push for heat pumps because it drops typically by a lot, about 4,500 watts to 800 watts. And therefore you get an energy efficiency value and you still get a time shiftable value. So that's just a really broad question. Would society as a whole benefit from a lot of water heaters being electric resistance and doing this versus heat pump? Much bigger question. And I think you're talking about addressing heat pump in the future.
Yeah, I think like control-wise, resistive water heaters and heat pump water heaters have their differences in terms of like how you design an algorithm. I mean, heat pump water heaters, you have like short cycling constraints that need to be taken into account, and like efficiency changes based on the water temperature. So efficiency goes down as you overheat it. So there's like more of a trade-off between efficiency and flexibility with heat pump water heaters compared to resistive water heaters. In terms of like which is best for society and like load shifting goals at large, that's more complicated. I think it probably depends on the local grid and your location and a lot of different variables. I mean, places where you have a lot of rooftop solar, like here in California, for a homeowner, it might make more sense to like invest in solar and then have a less efficient water heater where your water heater load all gets shifted to your solar. And so you're able to reduce emissions that way. But I think that varies a lot case by case.
Thanks.
I like that answer.
So, Lily, I think there's an opportunity for you and Dr. Bass to work together on some of the work he's doing. And I would put this out to the group. I was approached at AHR in Chicago, and I want to kind of get a sense. One of the manufacturers approached me and said, gosh, we'd like to know more about tank stratification and get a clarity on that. Is that something, Lily, that you find there's a lot of information about, or do we need more research in that area? Because you spent some time on that, obviously.
Yeah, I mean, in the like academic literature, there are a lot of papers looking at tank stratification and like developing models for that. So I think that is pretty well known in like academia. But I think the key point of our work was really figuring out how much you have to account for tank stratification in a controller, right? The model that you're using for the controller doesn't need to be as complicated as, you know, emulating stratification in a simulation. You basically like want the simplest model that still does good performance. And so figuring out what that is for different types of water heaters is a whole other thing. And so we've looked at 2-element resistive water heaters, but you know, for heat pump water heaters, there might be a different sort of model that you would want to use in this sort of optimization. And we haven't really figured that out yet. So I think on the controls, like model-based control side, there definitely is still more work to be done.
Okay, great. Any other questions before we open it up to other topics? And Lily, this was great. Thank you. I think it's the kind of stuff that everybody's curious about, and they want to. They love having other people do some of this great research, and if it's especially being open source, it really helps.
Yeah, thanks again. Awesome. So yeah, just open floor time. If anyone wants to raise any points about upcoming things that are related to advanced water heating, now's the perfect time.
And we're not wed to staying the whole time. So
Yep, exactly. If we end early, we end early, and that's all good. And don't have much in the way of next steps either. I'll just say that definitely excited for upcoming conferences like the Hot Water Forum, and should be a great time to keep seeing more cool presentations. Tristan, you have something?
Just a brief one, because I know
Yeah.
ending early sounds good. So I just maybe next time we can bring up all the efforts that are being done to sort of get the commercial water heating going. There's an AHRI 1390 group that's trying to do commercial grid signals and connectivity to HVAC. And boy, I've been trying to participate and help. And I think HVAC is so much more complex, especially at the commercial level. And, you know, does the thermostat provide enough, or do we really need to get signals to the equipment? So super complex. Whereas water heating, large commercial heat pump water heating, especially when the residential load profile is in place. So, you know, multifamily hotels are a little trickier. People take the showers at different times. But when we can shift large commercial, just simple water heating that follows residential load profiles, it's so simple compared to HVAC. So maybe we can get an update, you know, from you guys, Noah, Jeff, on that next connectivity group. I think because there's exciting things happening and it's changing every month.
Yeah, I love that. Great idea, Tristan. I think we can definitely put some space there. And if any speakers come to mind, if anyone here knows somebody who's specializing in commercial or central heat pump water heater load shifting, then super happy to give them the floor for a bit.
So NIA has contracted with Ecotope to come up with some proposed suggestions about that. So yes, absolutely, and Scott Spillman will do that.
Perfect. Well, I think we can wrap early. Again, this was recorded, so I'll send that out pretty shortly. later today, and then I'll also send out the slide decks. And I've been taking notes, so y'all will have that as well. Really appreciate the presentation again, Lily. Appreciate everybody who gave updates, and yeah, we'll see you next month. It'll be the same Friday on in March. So see y'all then.
See you there in ACEEE too. Bye-bye.
Thanks, everyone. Bye.